All right, this is the math handout for Chapter 12 and Chapter 17, which covers DC circuit capacitance. Okay, so we're going to begin to do the mathematical calculations on this circuit like we've done it on all of them. The first thing we're going to do is fill in our known values. So if you look on your math sheet here, we know that we have 36 volts total, and we know our three inductive reactance values, XC1, XC2, and XC3. And I'm sorry, that's not inductive reactance, that's capacitive reactance values. The next thing we want to do is calculate our total capacitive reactance. And we go about doing that by using our formula sheet. And since we are dealing with a series circuit, we will look at formulas 1, 2, 3, and 4 on our Chapter 12 and Chapter 17 formula handout. And we see here that Formula 3 shows us that capacitive reactance just adds up in series, the same way resistance did. So that tells us that we would have a total capacitive reactance of 2.4 k ohms. Now concerning voltage, current, and reactance, we can use Ohm's law, meaning if we can get 2 out of the 3 going horizontally, we can solve for the third. So we know that we have a total of 36 volts divided by 2.4 times 10 to the third, which is k ohms. Voltage divided by resistance gives us current, and that tells us we have 15 milliamps of current. Current stays the same in series, so we have 15 milliamps all the way down. Don't worry about these little slashes. That's just something that I had to put on there to know how to write up this sheet. Now that I've gotten my current, I can calculate out my voltages. So VC1 is equal to 15 milliamps times 400 ohms gives me 6 volts. I'll just do the same thing going all the way down, 12 volts, and finally 1.2 times 10 to the third, 18 volts. I've got all those calculations done. The next thing I have to calculate is my capacitance. I'm going to use this formula right here, which can be found on your capacitive Chapter 12, Chapter 17 formula sheet. And it tells me that my capacitance is equal to 1 over 2 pi fxc. So the first thing I want to do is hit my over under button right there. You see it highlighted in blue on the calculator. Just in case you missed it, let's do it again. Right here, over under, put 1, arrow down. I'm going to put 2. You're going to hit shift, hit your exponent button. Above it you see right here the pi symbol, times my frequency, which is found right here, 318.3 hertz. Be very careful because sometimes it's kilohertz. You see in the next problem it'll be k hertz, so don't forget the k if it's called for. But in this one it's just hertz. Times my total capacitive reactance of 2.4 times 10 to the third, giving me a total capacitance of 208.3. We round up the second number after the decimal place. Now my calculator in this case says nano, but in this particular set of problems we're going to always make our capacitive answers be in micro. So in order to make it go to micro, you have to hit shift engineering. If you hit shift engineering, it'll convert that number for you, giving you 208 microfarads. When I get ready to do the next one, I'm going to use this same formula. Everything stays the same except capacitive reactance. I just go up here and change it out. So I still got 2 pi times F times my next capacitive reactance value of 400, giving me a value of this. Hit engineering. That's already in micro, so he's good to go, 1.25 microfarads. On the next one, you scroll up, 800. Engineering gives you, okay, this one you got to hit shift engineering to get him in micro, 0.625 microfarads. And then finally you scroll up here, change this one to 1.2 k ohms, giving you a value of shift engineering 0.14, and we're going to round up the 6 to a 7, 0.417 microfarads. Okay, we're going to do the next problem here. Same process. First thing you do is fill in your known values. I know that I have 120 volts total voltage. In this case, they give me capacitance instead of reactance. So if they give me capacitance, I have to find reactance. If they give me reactance, I have to find capacitance. So in this case here, since they gave me capacitance, first thing I'm going to do is find my total capacitance. Then I'm going to use this formula to find my reactances. So my formula shows me that whenever I have capacitors in series, that I have to use the reciprocal formula, as you see right here, formula number 4. So that is done this way: 1 over under 1 over under 0.1 times 10 to the negative 6, scroll over, plus 1 over under 0.05 times 10 to the negative 6, scroll over, plus 1 over under 0.02 10 to the negative 6, giving me a total capacitance of shift engineering 0.0125 microfarads. Remember, all these answers have to be in micro, all capacitance answers. Now that I have my total capacitance, I can find my total capacitive reactance with this formula: 1 over under 2 shift pi times my frequency, 1.591 times 10 to the third times my capacitance. So the next thing I need to do is enter my total capacitance amount, 0.0125 times 10 to the negative 6 for micro. And that gives me a total capacitive reactance of 8K ohms. And then I'm going to go up here, change this number out to the value of C1 in order to find X1. So I just clear these numbers out and run the number again, and I just go through the whole scenario doing that. Now my next step would be to find my total current. I just use Ohm's law. Remember, you can use Ohm's law for these. So it's 120 volts over 8 times 10 to the third ohms, giving me a total current of 15 milliamps. Again, current stays the same in parallel. Current stays the same in series. So I can just keep it the same and enter them all in. Now it's just a matter of Ohm's law. V is equal to I times R, but in this case it's X. V is equal to I times X. I can just work my way down. So 15 milliamps times 1K ohms, 50 milliamps times 2K ohms, 50 milliamps times 5K ohms. Now we'll look at the parallel capacitive circuits. First step, as always, we fill in our known values. In a parallel circuit, voltage stays the same, so we automatically know all of our voltage values. Next thing we will do is fill in what we are given, which is the capacitive reactance values. We look at our formula sheet to determine how to find total capacitive reactance in a parallel circuit. And looking at our formula sheet here, it shows us that in parallel, you have to use a reciprocal formula to find total capacitive reactance. If you don't know how to do that, I showed it at the beginning of this video, or you can find a video specifically teaching that on my YouTube page. And that gives us a total capacitive reactance of 20 ohms. Now we can use Ohm's law to find all of our current values. 120 over under 20 gives us 6 amps, 1 amp, 2 amps, and 3 amps. All I'm doing there is just changing this bottom number to find each of my current values. When I want to find I2, I put in 60 ohms. Now that I have found all of that, I'm going to use my formula that I used before to find capacitance. And remember, I told you if they give you reactance, you have to find capacitance. So now I'm looking for capacitance. I'm looking for this formula right here. And so that's the one I will use. So C is equal to 1 over under 2 shift pi times, what is my frequency? 6.366 times 10 to the third times my total capacitive reactance of 20 ohms. And that gives me 1.25 microfarads. In order to find C1, all I'm going to do is go up here and change out this XC number to 120. Now remember, these have to be in micro, so hit Shift Engineering. 0.208 microfarads, 0.417 microfarads, and so forth. Alright, looking at the next problem here, we begin by filling in our known values, and this time they gave us capacitance. So the first step we're going to do, we look at our formula sheet in parallel, total capacitance, you just add them up. So now I have that number. If they give me capacitance, I have to find reactance. I do that by using this formula right here. And so I'm going to put this formula to use. 1 over under 2 shift pi times my frequency, and it's right here, 1.989 times 10 to the third times my capacitance, 1.45 times 10 to the negative 6, giving me 55.18 ohms. I go up here, I change out this last number, the capacitance number, to the new value, which is 240 ohms. I'm sorry, that was supposed to be 0.2, giving you 400 ohms. Scroll back up, we're going to change it to the next one, which is 0.25, giving me 320 ohms. Go back up, go to 1 microfarad, and 80 ohms. Now that I have all my ohms values, I can calculate out my current using Ohm's law. I is equal to V divided by X. So 24 volts divided by 55 ohms, 24 volts divided by 400 ohms, 24 volts divided by 320 ohms, 24 volts divided by 80 ohms. All right, next we're going to do our complex problems. On your formula sheet, you will see here, you have your series complex. So when you have a resistor and a capacitor in the same circuit, it's a series complex circuit. In order to calculate that circuit, you use only formulas 14, 15, 16, 17. When you have a resistor in parallel with a capacitor, that is known as a parallel complex. You use only formulas 18, 19, 20, 21, 22, and 23. You don't cross this line at all. Meaning if you're trying to calculate this type of circuit, you don't go over here and use any of these formulas, and vice versa. So we're going to begin as we always do by filling in our known values. We know our total voltage. Nope, we don't. But we know our current. And current stays the same in series, so we know all of our currents. And we know our resistors. and we know our capacitive reactance. So we're going to look on our formula sheet, and we're going to figure out which formula we need to use. So this shows us right here that we're going to use formula number 16. When you have resistance and capacitive reactance combined, it is called impedance. Impedance is a type of resistance to current flow, which is the combination of resistance and reactance. So total impedance is going to equal the square root, look at the calculator, I'm hitting square root, of R squared, which is 2 k ohms, squared, plus capacitive reactance squared, 1.5 times 10 to the third squared. The square root of those two numbers squared. Who figured that out? I have no idea. Giving us 2.5 k ohms. Yeah. So now we can figure out all of our voltage values. VT is going to equal IT times ZT, 20 milliamps times 2.5 times 10 to the third. 20 milliamps times 1.5 K, 20 milliamps times 2K. Very straightforward. The last thing we're going to calculate is this little OZ here, which is theta Z. In order to find theta Z, we will use formula number 17. And we see right here that what we have to do is inverse tangent. So tangent is right here, but we have to do inverse tangent, which is above it. So you go shift tangent. And the calculator should display tangent -1 open parentheses. Then you're going to hit the negative sign again. You're going to put XC, 1.5 times 10 to the third, over R, 2 k ohms. Scroll over, close it, hit equals, and it's -36.8. Round up the second number after the decimal place. 36.87, and this is degrees. Make sure you put the degree symbol. All right, let's work our next problem. We're going to begin the same way by filling in our known value of 36 volts. And what else do we know? We know our R value, 3.9 K. We don't know XC though, but they did give us capacitance. If they give us capacitance, we can find XC. How do we do that? With this formula right here. All we got to do is 1 over 2 pi F. What is F? Right here. What is C? Well, they gave it to us. It's right here. When we run that formula, it gives us 5 k ohms. Once we have XC and R, we can find ZT. Remember, it is the square root of, we had it right here, R squared, 3.9 times 10 to the third squared, plus 5 times 10 to the third squared, giving us an answer of 6.34 k ohms. Now I can find my total current by using Ohm's law. 36 divided by this resistance amount, this impedance amount. Current stays the same in series, so I got all my currents. Now I can use Ohm's law. V is equal to I times X. V is equal to I times R. I have all my values. The only thing left is to find theta Z. And that's going to be shift tangent minus, you're going to put the XC on top, over, scroll over, close parentheses, and remember that is degrees, -52.5. The next problems are complex parallel problems, and you will look at your formula sheet to see exactly which formulas to use, and as we discussed, it will be formulas 18 through 23 on your formula sheet. Remember, you can print your formula sheet from your Canvas page if you need a formula sheet, or you can always get one in class. So we know that we have 100 volts, and guess what? Voltage stays the same in parallel, so we got all of our voltages. We have our resistance, and we have our capacitive reactance. So when we get to this point right here, we have to be very careful, because the temptation is to go ahead and find impedance because you have these two numbers. But if we look closely at our formula sheet, it shows us that we have to use formula number 22. Because remember, you've got to stay on this side of this line when you're doing parallel. If you cross over here and you use formula 16, it will be the incorrect answer because 16 only applies to series. Right now we're doing parallel complex. So what we have to do is we have to find our current first. So we can find our current through our resistor using Ohm's law, 100 volts divided by 50 ohms. Our current through our capacitor, 100 volts divided by 25 ohms. Then we're going to use formula number 21 to get our total current. Total current is equal to the square root of IR squared plus IC squared. So we open up our square root right here. We put in our IR, 2 squared, plus our IC, 4 squared, equals 4.47. Now we can use formula number 22. ZT is equal to VA over IT, and VA is the same thing as VT, 100 volts over 4.47 amps, giving us a total impedance of 22.37 ohms. Finally, we have to find theta 1, and we find that using formula number 23, which is inverse tangent, shift tangent, and it's IC of 4 over IR of 2. Scroll over, close parentheses, and that is a degree measurement of 63.43 degrees. Now why don't you try to work the next one before you watch me do it? Okay, now that you've worked the next one, here's how I hope you worked it. We fill in our knowns. We know that we had 24 volts all the way down. We have our resistance, but we don't have our reactance. But if we have capacitance, we can use this formula to find reactance. Remember that you cannot at this point find impedance. You cannot find it. You got to do current first. Remember how we looked at all of this situation. So we're going to find IR using Ohm's law. IR using Ohm's law. We're going to find IC using Ohm's law. 24 divided by 500 gives you 48. 24 divided by 1.2 gives you 20. And then we're going to use our formula number 21 to find total current. Then we will use a fancy form of Ohm's law. ZT is equal to VT over IT. It's really nothing more than Ohm's law and a fancy formula, number 22, to find total impedance. And then finally, we will use our formula number 23 to find theta 1. This has been Math Handout, Chapter 12 and 17.